All right, hi everyone. Today what we're going to do is we're going to work on limits again because we're going to use limits on our next lesson as we look for the slope of a line. As we use our slope equation, right? And we're going to throw limits back into it. In the last class, you guys were asked to create the average rate of change. We also call that slope. And we threw an H in there, but we're going to go back to limits. So to do that lesson, we need to go back and learn this one. So what we're doing today is we're finding limits of problems that we could not find limits of before. Let me give you an example. The limit as, let's say, x approaches -4 of x squared plus 8x plus 16 over x minus 4. Oh, x plus 4, I'm sorry, x plus 4. Now, we went through a lesson just, I want to say 2 lessons ago, where we went ahead and just plugged in the limit, plugged in x and plugged in x. So let's go ahead and do that now and see what happens. If I plug in as x gets to -4, what does it look like at -4? Let's go plug it in. We end up with -4 squared plus 8 times -4 plus 16 over -4 times 4. Sorry, -4 plus 4. -4 plus 4. Okay. So we do the math. We end up with 16 minus 32 plus 16 over -4 plus 4. And that turns out to be 32 minus 32 over -4 plus 4. And you'll see that we end up with something called 0 over 0. And whenever we end up something called 0 plus 0, we have a new term for this. We're going to call this an indeterminate form. It's indeterminate. Now, indeterminate for us, maybe we don't need to use the word form, but indeterminate, let's use the word, just call it indeterminate. It's indeterminate, okay? And indeterminate tells us, wait, we got something going on here, right? So it's not that there's no answer right now, it's that we have a possibility of still finding the answer. Oftentimes when we divide by 0, like here we would end up dividing by 0, we say the answer is infinity, it does not exist, and we stop right there. But when we end up with 0 or 0, there's a hint that there is something up, that we can continue the problem if we just snoop a little bit more. Now, what do they want us to do? When you end up with 0 over 0, they want you to find another way. And I think it was find another way. Because there is probably another way. Find another way. Find another way out. You're trapped in a tunnel and the rocks have collapsed and you can't get out. And then what do? You just sit there and die? No, you try to find another way. If this entrance ain't gonna work, we gotta find another way. And you see movie after movie, they follow the breeze, they follow the water to find a way out. And lucky for them, they always get out, but we might not. So let's go ahead and find another way. And the other way here today is that if it's 0 over 0, there's a reason. And the reason why is you ended up plugging in the perfect value for x to make the problem go to 0. In this case, the top went to 0 and the bottom went to 0. That also refers to back when we were working on this at the beginning of the semester about factoring problems. If you end up with a 0, it means it's a factor. So why do I say that way? Because we have to now factor our problems. And when we end up with a polynomial x squared plus 8x plus 16 over x plus 4 as a limit as x approaches -4, we are going to factor this problem if possible. In this case, this polynomial is factorable. 2 numbers multiplied become 16, or 4 times 4. So we have x plus 4, x plus 4, I forgot the right limit, I'm sorry, all divided by x plus 4. And you will see now that we have a common factor on top and bottom. Now, if you remember, when we had this common factor, we call this a hole, and we do have a hole at the problem. Once we get rid of the hole, we can rewrite the limit as x approaches -4 as x plus 4. Now, if we plug in -4, we end up with -4 plus 4 is 0. We are no longer dividing by 0. Our answer is 0, and that's what the graph looks like. Let me go ahead and bring up Desmos for us to graph this graph. Let's pull up Desmos. And if I graph the original graph of x squared plus 8x plus 16, all divided by x plus 4. What does the graph look at like at negative 4? Let's go to negative 4 here. Here's negative 4. Here's negative 4. What does it look like? It looks like 0, doesn't it? The y value is sitting on the floor at negative 4. But what is the actual value there? Take a look. It actually does not exist. It's undefined. Why is it undefined? Because when I did plug in 0, we end up with 0 over 0. But what a limit is asking for is not what is it, it's what does it look like. And according to our human eyes here, that looks like a 4. Oh, sorry, that looks like a 0. Y is equal to 0. And that's the answer we got algebraically. So our idea here is that I can tell you what it looks like, even though the math says it doesn't exist, without having to graph it. The graph is just, again, to come back and prove to us in this visual way, easy way to say, hey, that's what the limit is. But we can do it without having to look up a graph. Now let's look at another problem. If I give you another problem, let's say the limit as x approaches 3 of x squared minus 9 over x minus 3. Let's see if this problem gives us a very similar result. First thing we're going to do is just try plugging it in. Maybe we'll get lucky. Maybe this will be an easy number. Maybe it'll just be like 5. But we won't know until we plug it in. We plug in 3 squared minus 9 over 3 minus 3. Please notice I don't write limit. Once you plug in x, you don't have to write limit. Right? Once you plug in x, you don't write limit anymore because we used it. Well, this becomes 9 minus 9 over 3 minus 3. Uh-oh, it's indeterminate again. We end up with 0 over 0. I'm sorry, I'm not sure what 0 over 0 over 0. It's indeterminate. Indeterminate means you can't determine it. Oh, I'm done. I'm walking away. No, you're not done. You haven't told me anything. You told me 0 over 0. That for us is indeterminate. Find another way. I'm not going to take no for an answer. You find another way. So let's go back and look at the problem. Well, in this case, I could factor x squared minus 9 as x plus 3, x minus 3 over x minus 3. Now for us, when it comes to a polynomial on top and polynomial on bottom, the idea is that if I end up with 0, 0, it means that there is a hidden factor. How do you end up with 0 through multiplication? It's because one of the factors was, take a look here, x minus 3. X minus 3 is 3 minus 3 is 0. That's how we end up with the 0 here. That's how we end up with the 0. X minus 3, which is 3 minus 3, that's how we ended up with the 0. The hint is that if you end up with 0 over 0, you know that the factor exists there. So we just have to spend some time finding it. Once we found it, we can now divide out our whole. The problem must be rewritten now as a limit as x approaches 3 of x plus 3. Okay, we're not done yet now because what does it look like when I plug in my 3? 3 plus 3. Please remember, I don't write limit anymore because I'm plugging it in. We end up with the number 6. That's what it should look like. Let's go ahead and check with Desmos. Hello, Desmos. Let's see if we come up with the same answer here. If I write x squared, x squared minus 9 divided by x minus 3. Let's take a look at the graph. We said, what does the graph look like at positive 3? Let's go over to positive 3. Here's positive 3. At 3, it looks like, oh no, it's undefined. Oh no, but look on the left side. At 2.9, it looks like 5.9. That's close to 6. On the right side, 3.01, that looks like 6. We're 6 on both sides, aren't we? So on the left side and the right side, they both say 6. All right, 6 it is. So not only does the graph prove that the calculable value, the one that we were able to get by hand, is accurate, we didn't have to actually graph it. We were only able to graph it so quickly because of Desmos. If not, we'd have to graph it by hand. Now, one thing is also cool is that all the other values, if I plugged in 2 or 1 or 6, those values would have come out just the same. Because we were able to reduce, we were good. Now, let me give you another example of this. If I give you something like 10 over 5, can you say that's just 2? 15 over 3 is 5, right? In essence, we are just reducing the problem. But if I end up with like 0 over 0, see how this really doesn't work for me? The 0, 0 doesn't really work for me because we are still dividing by 0. But what should it look like? It looks like 5, right? If I was able to divide it. Is it really there? No. The limit tells me what it should be, what it should look like, but in actuality, remember the point does not exist. It's a whole. Okay? It's really just a whole. So if it's a factorable problem, if it's a polynomial on top, polynomial on bottom, that's actually pretty one of our easiest cases, to tell you the truth. Now, does this ever happen with non-polynomials? Sure. And today we're going to go through the other ways, the other things we should be expecting when we see problems like this, okay? When we see problems like this, what else should we be expecting? Now, let me give you an easy one to start off with. If I give you a problem that says the limit as the limit as x approaches 0 of negative 2x over 2x plus 1 squared minus 1. Okay, so we're looking at a different type of problem that we will end up with 0 here. So if I plug in 0, this would be negative 2 times 0 over 2 times 0 plus 1 squared minus 1. This would be 0 on top over 1 squared minus 1 is just going to be 0, right? So we end up with 0, 0. Oh no, there's a 0 over 0 in this problem too. Well, can I factor this problem on my left? Does this look like a polynomial on top and on bottom? Take a look here. Give yourself a moment to look at it. Does it look like something that's factorable to us? Well, not really, right? And do you see the common factor that I could divide out? I see an x on top. That's probably my 0. Do I see an x floating around on bottom? The answer is no. So in this problem here, we're going to do our very best finding another way. We're not going to give up here. And one way is just to multiply it out. Let's just get rid of the parentheses. See what happens when I get rid of the parentheses. If I get rid of the parentheses, it'll be 4x squared plus 4x plus 1 minus 1. Take a look at what I did here. I square the front, square the back, and double the middle. That's one of the rules that you got to remember to do quickly, okay? 2x times 2x is 4x. 2x plus 2x is the 4x, and 1 times 1 is 1. Now, because we were able to multiply it out, hopefully you might see some like terms on the bottom. Let's see if we can see the like terms on the bottom. The 1 and negative 1. If I get rid of those, let's rewrite the problem now. The limit as x approaches 0 of negative 2x over 4x squared plus 4x. I'm going to go ahead and factor out some of these numbers that they become super obvious. We have the limit as x approaches 0 of negative 2x. On the bottom, you can see they have a 4 and x, don't they? So I'm going to take out the 4x, left over x plus 1. And we're going to go ahead and divide out our x's and 2's, okay? We're left over the limit as x approaches 2, sorry, x approaches 0 of negative 1 over 2 times x plus 1. So in this problem, we got rid of the variable that was giving us the 0. If I plugged in 0 here and here, 2 times 0 and 4 times 0, that's 0. That's our 0 over 0. And then so we took the vaccine and then we got rid of our coronavirus, right? That's gone now. And we have our negative 1 over 2 times x plus 1 left. Let's go ahead and plug in our 0 and see what happens to the graph, or see what the limit is if I plug in now 0, right? We're plugging 0 here. We end up with negative 1 over 2 times 0 plus 1. Take a look here. I don't write limit anymore because I plugged in the value. You don't have to write limit once you plug it in. And we're left with negative 1 over 2 times 1 is 2. So my guess is that at 0, my y value, what it should look like 1/2, negative 1/2. But is it? Let's go and take a look. Let's go ahead and throw it in our Desmos graphing calculator and see what we get. And this is just, again, this is us to just reaffirm what we've been saying here. Oops. Okay, let's go ahead and write that out. We're going to say it's negative 2x. Oops. Negative 2x. Let's see if that will work for us. We're going to divide that by parentheses 2x plus 1. Close it, and then we're going to square it. There you go, and then minus 1. Okay, so negative 2x squared. Okay, that looks right. Let's go and take a look at what does the graph look like at x is 0. Now take a look at x is 0. X is 0, does that look like 1/2 to you? Right. Ooh, here we go, 1/2, 1/2, 1/2, 1/2, 1/2, getting close. Oh, it's undefined. When x is 0, it's undefined. So when I tried plugging it originally, it gave me no answer, 0 over 0. It's indeterminate for us. Because when you divide by 0, we call it undefined in math in general. But what does the limit say? What should it have looked like? To me, it looks like on the left side, it says negative 0.51. That's 0.5. On the right side, negative 0.49. That's negative 0.5. It would look like negative 1/2, negative 0.5. We were able to do that without the use of a graphing calculator, algebraically. Okay, we got rid of our offending value, and then our factor was x. Then we were able to replug it back in to get the answer. Perfect. Now, we looked at when I have to factor. Maybe something you just have to multiply out, just throw it all out there. If you guys ever make models, you might just want to throw out all the pieces, or making puzzles, throw out all the pieces, and then start to organize afterwards. That's literally what we did. We threw out all the pieces, and then we started to organize. Now, the other one is rationalizing the denominator. That means this takes us back to our algebra 2 skill of multiplying these square roots away. So let's find a problem here. Let's try to find a problem. Okay, let's try this one. Okay, so we have the limit as t goes to 1 of the square root of t minus 1 over t minus 1. Now, all these skills you guys will be using in calculus, right? These are algebra 2 skills. We're really just reusing algebra 2 skills to help us solve for limits, something that we couldn't do before. Now let's go ahead and plug in our t value, plug in 1. That's going to be 1 square root of 1 minus 1 over 1 minus 1. Let's take a look and make sure that makes sense. We have plug in 1, t is 1. I don't write limits because we're plugging it in. That's going to be 1 minus 1 over 1 minus 1. We end up with 0 over 0. Indeterminate. Indeterminate means find another way, find another way, find another way. And when you see rationals, I don't want to find another way. It seems like it's going to be a lot of work. But we had worked on this in the class previously. And one way is what we're going to do is we're going to look for, let me talk about what the factor we need. If I plug in 1, well, how do you make this go to 0? It's 1 minus, sorry, I just wrote that again. It's going to be 1 minus 1, 1 minus 1. That's our factor. X minus 1 is our factor, right? Well, I have a t minus 1 already. I don't have a t minus 1 on top. So here is the gimmick. We're going to multiply this by our conjugate. The limit as t goes to 1 of the square root of t minus 1 over t minus 1. We're going to multiply the top and bottom. Let me use a different color here so you guys can see. Multiply by the conjugate. The conjugate of t, square root of t minus 1 is t plus 1, and square root of t plus 1. This is back from algebra 2. Now, here is a trick on the top. This is a pattern that we always have. It's a difference of 2 squares. If I say a plus b times a minus b, this becomes a squared minus b squared. No middle term, okay? No middle term. Because let's write out a squared plus ab minus ab minus b squared. Take a look here. The middle term always ends up canceling out. They're opposite signs. So we just square the front and square the back. Excuse me. Okay, so let's go ahead and multiply this out. So giving that hint, and it's a little bit odd hint, but we just have to square the front, which is t. we square the back, -1, over, hey, that's exactly what we wanted. And we just multiply the bottom. Please do not do anything except just copy it on the bottom. We're just going to copy that here. Do not try multiplying it out. And you will hopefully see we automatically have a factor that we're going to divide out. But a factor that we can get rid of. So here we go. Since we delete that, we have the limit as t goes to 1 of 1 over the square root of t plus 1. Excellent. Plug in the 1. 1 over the square root of 1 plus 1 is 1 over 1 plus 1, which is 1 over 2. So the idea here is when I first initially tried to plug in my variable, it rejected it. Okay, I asked the girl out, she rejected me. Does that mean you stop? It means, well, okay, don't be creepy. I'm not saying be creepy, but come about it another way. Be a little nicer. Maybe try a different angle, right? And that's what's happening here. And is the answer going to be 1/2? Well, let's go ahead and take a look. Let's go ahead and graph this one more time. So we're going to take the square root. I don't have a square root symbol. Oh, I do have a square root. Square root of t. Let's go ahead and put that in parentheses, actually. T minus 1 divided by t minus 1. Okay, so we're given a graph here. What does the graph look like at 1? Take a look here at 1. You guys see 1 right there, 1's right there, right in the center. The graph at 1 looks like 0.9, oh, 0.5. And you can see right there, it doesn't exist, does it? Right, it's undefined. So when I plugged in the value, it wasn't able to tell me at all what that y value was. But since it was indeterminate, I was able to try a skill such as rationalizing the denominator, multiplying by the conjugate. That turned out to reveal the hidden factor. It revealed the hidden factor. And then after we were able to divide out those factors, those common factors, we were able to plug back in the limit, giving it another try, and then we were able to find out what the value is, 1/2. That's what it looks like. And as you can see in the graph, it looks like 0.5. Okay, so we will discuss 3 different ways of finding limits of these rationals, these fraction problems. If it doesn't work right away, if we end up with a 0 over 0, that's a fancy word called indeterminate. And that's our indeterminate. Once it's indeterminate, we got to try another way. We tried through 3 different ways today. We've tried 1 by factoring. A second way is by multiplying it out. And our third way is rationalizing. Usually we call it rationalizing the denominator. But in this case, it was actually the numerator, right? So we're just rationalization, okay? We're trying to make that square root into a whole number, which is what we ended up doing. We made that square root into that whole number, rationalizing. Okay, all right, and that's it.